Welcome, Calculus 2 students. We are looking at numerical integration today. We use computers and calculators to do what's called numerical integration. Sometimes because we have a lot of data points and we want the integral because we have data points, or we have some sort of integral that can't be integrated with our regular techniques. So we use computer software, we use a calculator to get that integral value. When we're doing this, we will get errors. These errors are either an absolute error or they're a relative error, and we are going to calculate the values for each of those using in relationship to pi. And the ancient Greeks used 22/7 as their approximate value of pi, and we're going to figure out what the error on this is. And what we're going to do is just plug in what we're using for our approximation, which is 22/7 minus that value of pi. Now we're just going to use our calculator's approximation of pi, and if we chunk that into our calculator, what we'll end up with is 0.00126. Now in order to get the relative error, we're going to do the 22/7 minus pi over this calculator's value of pi, and I'm just going to use that for my calculator, and it's going to get approximately, of course I need to use these wavy brackets, 0.000402. In other words, this is about 0.04%, which is a pretty good approximation. Next, we're going to look at examples to find these numerical integration values. We're going to start this with an extension really of the Riemann sums. You probably recall doing a left and right-handed Riemann sum, and we found the area of each of those rectangles and added those up. In this case, we're just going to find, we're going to figure out how many intervals that we're going to have, or subintervals that we'll have, and we'll calculate the midpoint of each of those rectangles, and we will use that in our calculation of area of each of these rectangles, and then we will add all of those up, very similar to the left and the right Riemann sum. So this particular example shows you the x squared. We're supposed to calculate the area from 2 to 4, and we will be using this midpoint as our value on the height of our rectangle, and then the width of this would then be, because we've broken it up into 4 subintervals between 2 and 4, each one would then be a half in length. So let's write that down. Alright, I have computed the width of each of my subintervals, which I talked about, and that is a half. And here is the computation given from this equation right here. And my midpoint approximation, I will go in the middle of each of those subintervals. So between 2 and 2.5, the middle of that would be 2 1/4. So I need to find that function value at 2 1/4, and then I need to multiply by that delta x, which is the width of each subinterval. So I'll go and get each of those values for you. Alright, this is just a computation with no calculus involved, and I get 18.625 if I break this into 4 subintervals. Next, I'll need to break this into 8 subintervals, so that delta x will then be, and I believe it's still 4 to 2, so that'll be 4 minus 2 divided by 8, so each delta x will then be 1/4. So I'm going to need to find the midpoint between 2 and 2 1/4, and then add all of those up, each of those values. So I'll do the same exact thing, but this time with double the number of subintervals. Alright, now I really don't want to do this for 8 subintervals, so I'm going to figure out a way to do this with my calculator. So I'm going to do this summation, and I get there by hitting my math button and then going to summation, and this is what I get. Now I'm going to write things in terms of x. So what I'm going to do is I'm going to have an x here, and I need to figure out what it is that I need to put in this thing, because I can see that my calculator will do that for me without me having to go through and manually write this down, especially if you have a lot of homework. So I'm going to figure out how to get this 4 subintervals, and then I'll extend that to 8. Alright, so if I'm going to punch this in my calculator, I'm going to write x equals 1 to 8. Oops, I want 4. Sorry for this first. Okay, that looks better. So I'm going to do this from 1 to 4, and I'm going to make sure that I get this 18.625. Alright, so here I go, 1 to 4. My x of k needs to be my a, which is my lower limit, so that's a 2 in this case, plus my number of subintervals, so this is subinterval number 1, so I'm choosing that to be x in this case, so don't get confused because I've got x as being 2 different things here, so I have to be careful. And then my delta x I've already computed, and it was the 0.5, so I'll just write that in. So in my midpoint formula I need x of k minus 1 plus x of k. Well, I've got x of k, so x of k minus 1 would then just be 2 plus, and then this would just be x minus 1 times that 0.5. So that's what I need to plug in, so I'm going to write it out to the side here. Alright, after plugging that into my calculator, I get 18.625, which was what I wanted. Now, if I want to extend this to 8 subintervals, all I have to do is go into my calculator and copy that command that I just entered, knowing that it's right, and then change this top right here to an 8, and then get my answer. Alright, so I changed it to an 8. I changed each of those delta x's, which delta x for 8 subintervals is 0.25, so you'll notice each one of those I changed to 0.25. That's where I have circled here, and I get m of 8 is 18.65625, and makes it much easier. The hard work is just getting it set up, and once you've got it set up, then it makes it easy, especially if they're going to make you do 4 and 8 and whatever number of subintervals. So I'm just following that formula and plugging it into my calculator. We extend the Riemann sum a little bit more. Instead of a left, right, or a midpoint, now we're going to do the trapezoidal rule. And notice if I made trapezoids of each of these subintervals, that's going to be pretty darn close. And a trapezoid, in order to find that area, is going to be following this formula, which just follows from finding the area of a trapezoid. And I'll just follow this formula and see what I get. If they would have asked me to do 4 and 8 and another set of subintervals, I probably would have plugged it into my calculator, but I'm a little too lazy for that. So since they only want 4 subintervals, pretty straightforward. I'm just going to do this grunt-wise and just do it by hand. I need to know each of these x of k's. So I found that delta x was 0.5, x naught is my beginning point. So that would be at a 2, add to that to get my next one, the 0.5, and so forth. So now I'm just going to plug into this formula because I believe I have everything I need. Alright, and this gets even closer to my actual value for the integral of x squared from 2 to 4. Let's find out what that really is. Okay, so there's what the exact value is, and increasing that the number of subintervals will just get you closer and closer to this value of 18.66. Looks like my midpoint was a little closer in this trapezoid, but increasing that in will make it closer and closer to the actual value. Alright, in order to find the errors in the midpoint and trapezoidal rules, you do have to know the exact value of the integral. Note they gave you the exact value of the integral here. It is 1 minus 2e to the negative 1. We could have figured that out, but it is known. Now, in order to get midpoint and trapezoidal rule approximations, I would actually have to do each of these, and I'm not going to do that in this video, just in the interest of time. but if I would do that as I did the previous example where I showed you how to plug it in on the calculator, and it does take some doing in order to get that midpoint or the trapezoidal rule. I would just do it just as I did before. If you would, you can see those errors in each of those approximations, and you can see that the errors are decreasing with increasing in, which was the point of this example. Alright, getting this problem set up, it's a bunch of data points, and I'm supposed to use the midpoint trapezoidal rules to estimate what the value is. So I'm wanting this from, I'm going to go ahead and label these t equals 0 is year 1992 and t equals 16 is year 2008. So I basically want this flow from 0 to 16 of this r of t dt. So I want that value, and I'm going to approximate this q is going to be approximated by the midpoint with 4 subintervals because, well, we don't want to do too many more than this. So the middle of each of these is going to be at r of 2 plus r of 6 plus r of 10 plus r of 14. And then that's going to be my heights, and then I'm going to multiply it by the widths, and my widths of this would be that delta t, and since I am dividing the 16 into 4 subintervals, that delta t would then be a 4. So when you plug all of these in, let me write that down, I'll get 385.2, and that's just writing each of those heights times that width and adding them up. Alright, this is what it would be for using the trapezoidal approximation, and I'm just going to key in each of these. The first and last point will be taking the average according to the trapezoidal, according to finding the trapezoidal area is what I'm just using that rule. Alright, in this next example we have Simpson's rule, and Simpson's rule is a combination of the trapezoidal rule. So I would have to do the trapezoidal rule for 2 different subintervals, and I probably would use a calculator or computer to do this, and you'll notice this is done with a computer software. And once you have that value, and if you know the exact value of the integral, then you can compute the error which was done in this table. So I would just plug this into a computer software or calculator just as I did in the previous example, and then compute my errors for each of those different subintervals. And if you're asked to do more than just a 4 or an 8 subinterval, then I definitely go ahead and plug it into computer software. I'm not going to do 16 subintervals by hand. The next is just a theorem having to do with the error, and once again, this is your error using that Simpson's rule. Alright, if you have any questions about this, please contact me by email, and if you want to know how to use some of your computer software, let me know too. And seeing as I don't know what computer software you have, you'll have to let me know what you have, and then we'll go from there. Alright, see you at the Collaborate.